I'm gonna open up the Patreon and the Discord, and then I'm actually gonna do a giveaway where one of the lucky people who signs up is going to get a free Figure 69 Anthony Makes Videos cone t-shirt. Yeah, my laptop is now sitting on top of a copy of Gravitation, Misner, Thorne and Wheeler that I got on Amazon. Here we go. This is a real conversation starter, though. We have another Vanderhagen the Stampede comment here. Are the terms fundamental and form used appropriately? This is definitely a very good philosophical and linguistic issue that Vanderhagen the Stampede is bringing up here. This kind of thinking abstractly is rife throughout mathematics, and Carl Friedrich Gauss is no exception to this. Okay, this is suspicious because we have a minus, but then on the next line we have another minus, which kind of seems like a typo, but anyways, I haven't checked this math by hand, obviously, so don't yell at me in the comments. Again, where we have these equations running over multiple lines and we have a minus followed by, on the next line, another minus, which, if you know anything about math, negative times a negative equals a positive. Subtracting a negative is the same as adding the magnitude of that negative value. This is elementary school arithmetic here, but anyways, salut tout le monde. Welcome back, Differential Geometry gang. If you're new, I'm Anthony, obviously, and this is episode 31 of my series where I, Anthony, read Differential Geometry by Erwin Kreisig out loud for you guys. And thanks for everyone liking my video on the way in, because that really helps to encourage the algorithm to push my content out there for more people, and so I really appreciate you guys doing that. And shout out to everyone who's just listening to these, whether that's in the background while you do something else or you listen to it to fall asleep. Whatever it may be, I definitely keep all of you listeners out there in mind when I make these. So shout out to the listeners. And with this being said, what you are currently watching or listening to is not a class, this is not a course, this is not a podcast, this is not a lecture, and this is not necessarily an unofficial math audiobook of Differential Geometry by Erwin Kreisig. But part of the purpose, I think, for making these videos is for me to remember and recite math through the act of taking the sentences, the equations, and symbols that are printed, if you really think about it, on the dead trees in this book, and bringing them to life by reading them out loud. And I hope that when you watch, listen, or you read along, that these videos foster connection or provide guidance to you in some way. And I hope that these videos serve as contributing to our collective building of a sort of anchor for differential geometry on the internet right now, around the clock, around the world. And I also hope that these videos inspire others with a sense of the importance of habitual devotion to the serious study and reading of books. And on that note, I encourage all of you, if you don't do this or haven't already, to build a house of books. Books that you enjoy, books that you want to read, books that you can read. And I hope that however you consume this video, that it helps you foster an atmosphere of devotion to following the path that you feel personally called from the transcendental to follow in order for you to self-actualize. And so regardless of where you are on your path right now, I'm glad to have you here while we read about differential geometry and think about the philosophy and the physics of it all. Section 71. Absolute differentiation of tensors of arbitrary order. By a simple generalization of the investigations carried out in the preceding section, we shall now obtain the definition of the absolute derivative of a tensor of higher order. The different steps of our reasoning will be exactly the same as those of that section. We have to start from the transformation law of an arbitrary tensor, that is, from equation 30.5. To every index of the tensor there corresponds in every term of the multiple sum on the right-hand side of this transformation law exactly one first-order partial derivative. For example, the transformation law of a mixed tensor of second order is given by a over bar sub alpha superscript tau equals a sub beta superscript zeta times partial u beta partial u over bar alpha, then times partial u over bar tau partial u zeta. It involves two such partial derivatives in every term of the double sum on the right-hand side. The first step consists in differentiating the transformation law of an arbitrary tensor, u1 over bar or u2 over bar. When doing so, each of the aforementioned derivatives yields one second-order partial derivative in each term on the right-hand side. In our example, we thus obtain partial a over bar sub alpha superscript tau partial u over bar rho equals partial a sub beta superscript zeta partial u sigma, then times partial u sigma partial u over bar rho, then times partial u beta partial u over bar alpha, then times partial u over bar tau partial u zeta, plus a sub mu superscript nu, then times the quantity partial squared u mu partial u over bar alpha partial u over bar rho, then times partial u over bar tau partial u nu, plus partial u mu partial u over bar alpha, then times partial square u over bar tau partial u nu partial u sigma, then times partial u sigma partial u over bar rho closed quantity. The second step consists in eliminating each of these second derivatives by means of the transformation law of the Christoffel symbols previously given in section 47, which there's actually kind of two of them. And we can refer back to 70.1, which is in the previous section, where we had put these second derivatives into the transformation laws for the Christoffel symbols. In this manner, we obtain in our example, instead of the bracket on the right-hand side of what is previously given in 71.1, the expression quantity Christoffel over bar sub alpha beta superscript gamma, then times partial u mu partial u over bar gamma minus Christoffel sub beta sigma superscript mu, then times partial u beta partial u over bar alpha, then times partial u sigma partial u over bar rho closed quantity, then times partial u over bar tau partial u nu, plus quantity Christoffel sub mu sigma superscript zeta, then times partial u over bar tau partial u zeta minus Christoffel over bar sub epsilon lambda superscript tau, then times partial u over bar epsilon partial u nu, partial u over bar lambda partial u sigma, closed quantity, then times partial u mu partial u over bar alpha, then times partial u sigma partial u over bar rho. We have now to order the expression thus obtained. All sums of products which involve Christoffel symbols, namely Christoffel over bar sub alpha beta superscript gamma, corresponding to the coordinates u over bar 1 and u over bar 2, are transposed to the left-hand side of the expression under consideration. When doing so, all tensor components which occur in those products and correspond to the coordinates u1 and u2 are transformed into tensor components corresponding to u over bar 1 and u over bar 2. This can be done by means of the previously given 30.5, which, like I said, is that arbitrary tensor transformation law, and leads to terms which no longer involve first partial derivatives. Consequently, no such partial derivatives appear on the left-hand side afterwards. Since a sub mu superscript nu, then times partial u mu partial u over bar gamma, then times partial u over bar tau partial u nu equals a over bar sub gamma superscript tau, and furthermore, a sub mu superscript nu, then times partial u over bar epsilon partial u nu, then times partial u over bar lambda partial u sigma, then times partial u mu partial u over bar alpha, then times partial u sigma partial u over bar rho equals a over bar sub alpha superscript epsilon, then times Kronecker delta over bar sub rho superscript lambda. We thus obtain in our example partial a over bar sub alpha superscript tau partial u over bar rho minus a over bar sub gamma superscript tau, then times Christoffel over bar sub alpha rho superscript gamma plus a over bar sub alpha superscript epsilon, then times Christoffel over bar sub epsilon rho superscript tau equals the quantity partial a sub beta superscript zeta partial u sigma minus a sub mu superscript zeta, then times Christoffel sub beta sigma superscript mu plus a sub beta superscript nu, then times Christoffel sub nu sigma superscript zeta closed quantity times partial u sigma partial u over bar rho, then times partial u beta partial u over bar alpha, then times partial u over bar tau partial u zeta. Also in the general case, to every index of the tensor, there corresponds exactly one multiple sum of additional terms on each side of the expression obtained by the above ordering process. Every one of these sums has a positive... oh my goodness. Okay, Mr. Wild Boy. Every one of these sums, he frustrated, he mad. All right, I'm getting attacked by a black super predator. That's how it's going to be. Every one of these sums has a positive sign if it corresponds to a contravariant index and a negative one if it corresponds to a covariant one. We have already come across a special case of this fact in the preceding section. In the case of our example that follows from the expression above, that the quantities a sub beta superscript zeta, but then that itself has a subscript comma sigma. And this notation follows from what is given in the previous section. Hopefully I'll have that on the screen right now. But in any case, this is equal to partial a sub beta superscript zeta partial u sigma minus a sub mu superscript zeta then times Christoffel sub beta sigma superscript mu plus a sub beta superscript nu then times Christoffel sub nu sigma superscript zeta. And these quantities are the components of a tensor of third order. That is, covariant of second order and contravariant of first order. This tensor is called the covariant derivative of the tensor a sub beta superscript zeta with respect to the tensor g sub alpha beta. In the case of a tensor a sub alpha 1 through alpha r and superscript beta 1 through beta s of order r plus s, covariant of order r and contravariant of order s that is, we find that the quantities a sub alpha 1 through alpha r superscript beta 1 through beta s, and then that tensor with the covariant alpha indices and the contravariant beta indices, that tensor then has a subscript of comma sigma. That is equal to partial a sub alpha 1 through alpha r superscript beta 1 through beta s partial u sigma minus a sum on the index gamma from 1 to r of a with subscripts alpha 1 through alpha gamma minus 1, and then kappa, and then alpha gamma plus 1 through alpha r, and then we have superscripts beta 1 through beta s, then times Christoffel sub alpha gamma sigma superscript kappa plus a sum on delta from 1 to s of a with subscript alpha 1 through alpha r, and then superscripts beta 1 through beta delta minus 1, and then lambda, and then beta delta plus 1 through beta s, then times within the sum, of course, Christoffel sub lambda sigma superscript beta delta. Okay, that got a little butchered, but at any rate, these quantities are the components of a tensor of order r plus s plus 1, that is, covariant of order r plus 1 and contravariant of order s, and this tensor is called the covariant derivative of the tensor a sub alpha 1 through alpha r superscript beta 1 through beta s with respect to the tensor g sub alpha beta. In consequence of the covariant differentiation, the number of the covariant indices increases by 1. The covariant derivative of a differentiable tensor of order 0, that is, of a scalar phi in terms of coordinates u1 and u2, is defined by phi with a subscript comma sigma is equal to partial phi partial u sigma. This covariant vector phi sub comma sigma is called the gradient of the scalar phi. And we can refer back to section 29 because I believe we already mentioned this before. We finally mentioned two cases of the above covariant derivative of the tensor A with respect to the tensor G sub alpha beta, which occur frequently. In the case of a covariant tensor of second order, let's say A sub alpha beta, the covariant derivative takes the form A sub alpha beta comma sigma is equal to partial A sub alpha beta partial U sigma minus A sub gamma beta then times Christoffel sub alpha sigma superscript gamma minus A sub alpha gamma times Christoffel sub beta sigma superscript gamma. The covariant derivative of a contravariant tensor of second order, say A superscript alpha beta, is given by A superscript alpha beta, and then that tensor, A with those contravariant superscript indices, then has a subscript, comma sigma, then that is equal to partial a superscript alpha beta partial u sigma plus a superscript gamma beta then times Christoffel sub gamma sigma superscript alpha plus a superscript alpha gamma then times Christoffel sub gamma sigma superscript beta. The covariant derivative of a mixed tensor of second order is of the form previously given in the expression for a sub alpha beta comma sigma. And now we are at section 72, further properties of absolute differentiation. As can be immediately seen from the expressions for the covariant derivatives of these tensors previously given, the covariant differentiation of sums and products is governed by the same formal rules as those that govern the usual differentiation. A sum of tensors, which, by the definition of addition of tensors, must be of the same type, may be differentiated term by term. For instance, we're looking at the sum of two tensors in a quantity. The tensors are a and b, but then of course they have covariant and contravariant indices. And this sum then has a subscript comma sigma, but read all out here we have the quantity a sub alpha 1 through alpha r superscript beta 1 through beta s plus b sub kappa 1 through kappa r superscript lambda 1 through lambda s closed quantity subscript comma sigma is equal to then a sub alpha 1 through alpha r superscript beta 1 through beta s and then subscript comma sigma plus b sub kappa 1 through kappa r superscript lambda 1 through lambda s and then subscript comma sigma. The covariant differentiation of a product of arbitrary tensors is governed by the elementary product rule. For example, likewise as above, we have within the quantity two tensors, C and D, and then that product has a subscript comma sigma. And now I'm going to read it all out with the indices for the tensors C and D. So we have the quantity C sub mu1 through mu p, superscript mu1 through mu q, then times d sub pi 1 through pi r, superscript rho 1 through rho s, closed quantity, subscript comma sigma is equal to c sub mu1 through mu p, superscript mu1 through mu q, and then that tensor C has a subscript comma sigma, and then that is times the tensor D with a subscript pi 1 through pi r, superscript rho 1 through rho s, plus c sub mu 1 through mu p, superscript mu 1 through mu q, then times the tensor D with subscripts pi 1 through pi r, and then superscript rho 1 through rho s, and then that entire tensor has a subscript comma sigma. For example, in the case of a product of the tensors a sub alpha beta and b superscript rho sigma, we obtain the covariant derivative in the form quantity a sub alpha beta then times b superscript rho sigma and then closed quantity subscript comma kappa, which is then equal to partial u kappa of a sub alpha beta times b superscript rho sigma, closed quantity, then minus b superscript rho sigma, then times the quantity a sub gamma beta times Christoffel sub alpha kappa superscript gamma plus a sub alpha gamma times Christoffel sub beta kappa superscript gamma, closed quantity. And then we have plus a sub alpha beta, then times the quantity b superscript gamma sigma, then times Christoffel sub gamma kappa superscript rho plus b superscript rho gamma, then times Christoffel sub gamma kappa superscript sigma, closed quantity. Hence, the product of a sub alpha beta with b superscript rho sigma, all having a subscript comma kappa, is equal to a sub alpha beta comma kappa then times b superscript rho sigma plus a sub alpha beta times b superscript rho sigma, all having then a subscript of comma kappa. In the above expression that I just read, if we set beta equal to rho, we obtain the covariant derivative of the inner product of the given tensors in the form a sub alpha rho times b superscript rho sigma, all then having a subscript of comma kappa, equal to a sub alpha rho comma kappa then times b superscript rho sigma plus a sub alpha rho then times b superscript rho sigma, all having a subscript of comma kappa. The tensors g sub alpha beta, g superscript alpha beta, and delta sub alpha superscript beta behave with respect to covariant differentiation in the same manner as constants with respect to the usual differentiation. Indeed, we have the following, which is due to Giorgio Ricci Cubastro, or we just call him Ricci. Theorem 72.1. The covariant derivatives of the tensors g sub alpha beta, g superscript alpha beta, and delta sub alpha superscript beta are zero tensors. And the proof is as follows. In consequence of the previously given expression for the covariant derivative of the tensor a sub alpha 1 through alpha r superscript beta 1 through beta s that we had earlier, we obtain g sub alpha beta comma kappa is equal to partial g sub alpha beta partial u superscript kappa minus g sub gamma beta then times Christoffel sub alpha kappa superscript gamma minus g sub alpha gamma then times Christoffel sub beta kappa superscript gamma, which is then equal to partial g sub alpha beta partial u superscript kappa minus the quantity Christoffel sub alpha kappa beta plus Christoffel sub beta kappa alpha closed quantity. Hence, by the expression for the sum of two Christoffel symbols of the first kind, which was given previously in section 47, g sub alpha beta comma kappa is equal to 0. Furthermore, by the expression for the covariant derivative of a contravariant tensor of second order, which I read earlier, g superscript alpha beta and then a subscript of comma kappa is equal to partial g superscript alpha beta partial u superscript kappa, then plus g superscript gamma beta then times Christoffel sub gamma kappa superscript alpha plus g superscript alpha gamma times Christoffel sub gamma kappa superscript beta. In consequence of the previously given property of the Christoffel symbols from section 47, I'll have it on screen right now, hopefully, these expressions vanish. Finally, we obtain from another one of those covariant derivatives which I read earlier, we have delta sub alpha superscript beta and then subscript comma kappa is equal to partial delta sub alpha superscript beta partial u superscript kappa plus delta sub alpha superscript gamma then times Christoffel sub gamma kappa superscript beta minus delta sub gamma superscript beta then times Christoffel sub alpha kappa superscript gamma is equal to Christoffel sub alpha kappa superscript beta minus Christoffel sub alpha kappa superscript beta, which is equal to 0. From the previously given definition for the gradient of scalar phi, we obtain the second covariant derivative of a scalar phi in terms of u1 and u2, which is of class r greater than or equal to 2, that is to say it is at least 2 times differentiable, and then when we're almost there, we have at least one derivative that does not go away to 0, in the form phi sub comma sigma lambda equals partial square phi partial u superscript sigma partial u superscript lambda minus partial phi partial u superscript tau then times Christoffel sub sigma lambda superscript tau. Consequently, we may write the formulae of Gauss, which we first saw in section 45, in the form x sub I comma alpha beta is equal to b sub alpha beta times n sub I, where I is equal to 1, 2, or 3. And we can also write the formulae of Minardi-Codazzi, which we first saw in section 46. We can rewrite the formulae of Minardi-Codazzi in the form b sub alpha beta comma gamma is equal to b sub alpha gamma comma beta. And now we're going to do a break before I finish reading section 73. All right, I just finished editing this video that you're now watching, and I realized that I didn't even talk about the Patreon, the Discord, and the merch. So I'm going to set all of this up, but this is how it's going to work. I'm really looking forward to starting the Discord, but there are some problems that I'm already sort of anticipating. One is I don't want to open it up and for there to be like 5 people who join, and then the activity kind of wanes off, and then maybe like 5 more people join, but those first 5 people stopped after their first little burst of activity, and so then the server really just never takes off. Oh, another thing is that I'm going to have some rules, obviously, and I don't have like the whole culture of this group worked out already, but for sure I'm only going to allow people who have profile pictures which are real pictures of your real human face. So no anime profile pictures, no AI generated pictures. You also have to be using a username which is like a real name. It could be a nickname or something, but I'm not gonna call you like some alphanumeric screen name that you have. So yeah, don't sign up for this if you have some sus anonymous account that you use to surf the dark web or something. But I also want to prevent there from being bots from entering. So that's kind of where the Patreon comes in. I don't really want to make this channel into like a cash grab from you guys or anything like that. Like, it's really important to me that I stick to being authentic and stuff, because from the time I've spent on YouTube, that's what I'm really most looking out for. And like, I can tell when people are fake instantly, you know what I'm saying? So like, I'm not trying to do that to you guys, just, you know, trying to rip you guys off, trying to have a passive, you know, income that I gain from this. No, that's not what this is supposed to be. So, but the Patreon is going to be, I don't know, something low and affordable, just so that I can prevent bots from joining. But I'm trying to work out a way that I can kind of economically incentivize people to not be lurkers. I'm not sure if on Patreon I can suddenly make your subscription go from like $1 to $5 if you're a lurker and you're not posting on the Discord. It might actually turn out to be the other way, where it's like you sign up and it's like $5, and then maybe you'll get discounted or get like 3 months back if you're posting actively on the Discord. Because that's what I'm trying to avoid, is like people who just like join and then they just read posts but they never interact or anything like that. So like, I'm going to be encouraging you guys on the Discord to actually join video and voice chat, and like, we're actually going to, you know, interact face to face in that way, not hiding behind freaking fake names, out, you know, anime profile pictures and all that kind of crap. You know what I'm saying? But hopefully, if I have my act together, then in the description below, there will be like a Google survey of some sort, where once I hit a threshold of a number of people interested in these things, I'm going to open up the Patreon and the Discord, and then I'm actually going to do a giveaway where one of the lucky people who signs up is going to get a free Figure 69 Anthony Makes Videos cone t-shirt, and I'm going to contact you. We'll get your shirt size and your shipping info, and I'm going to send that out to you, and it's going to be great. It's kind of going to be like also a way for me to just test out finalizing the delivery service for getting these shirts out there for you guys. So with that being said, back to the video. Now I'm going to keep this short because I usually do these rants in the intro in the beginning here, but this is like the third time that I've sat down to record this episode now. Honestly, the first take, what I was going to do is read sections 71 and 72, and then stop and then do the typical ranting and react to viewer comments. And then I was going to read 2 more sections, 73 and 74. And the last times that I filmed this, the takes were really not good. I mean, I was kind of a little bit sick. I get like kind of like seasonal sickness, seasonal depression. I don't want you to think it's like despair or sadness, but it's like depression in the sense of like my immune system gets a little bit suppressed during the winter and stuff like that. So like my voice was kind of hoarse. So I'm keeping the reading takes from that. But the other thing was that section 74 is on the Bianchi identities, and I think I'm going to spin that off into its own video. And then part of what I was ranting about for in between after reading section 71 and 72, I was going to try to like recap a review of like the Einstein summation notation, Christoffel symbols, and tensors, because I do think about how there are people who watch these videos for the first time and they haven't watched any of the other differential geometry videos that I've made. Those people aren't really familiar with differential geometry in general to begin with. So the notation is definitely a barrier to entry in order to understand this stuff. So I was going to do like a review of that stuff in this video, but kind of like the Bianchi identities stuff, I'm deciding to spin that off into another video as well. Anyways, I'm probably editing this to be in between reading 71, 72, and then after this I'm going to read section 73, and then I'm going to end this video. So let's get into the comments here. Yeah, this is definitely, like I said, one of my favorite segments of these videos, as it turns out, is reading your guys' comments here. So we have on episode 30 from Magma Baby. When will the full song be on Spotify? I need it to study differential geometry. Good question. I've actually been thinking of like turning these rap intros into like a mixtape, and then maybe towards the end of this I'll put that on Spotify or something. But the big problem I have is finding good beats, especially beats that won't get me copyright flagged or whatever on YouTube. So if you guys have any beats, send them my way. We've got from Trav the White, good to see you, Trav the White, fire at the beginning. I hope that I impressed Trav the White with my bars because, you know, like 6 months ago, 7 months ago, or maybe before that, Trav the White told me in another comment, he was like, you know, you need to study different types of flows and stuff like that. And I took it to heart, and I feel like I hope that paid off in my last video. So thank you, Trav the White. We've got a very useful comment here from Howie G. I think a better place to understand general relativity is, and then we've got some links here. So you guys should definitely check those out. I'm probably going to pin that after I film this if it's not pinned already. We got one in the standalone video for In Fundamental Forms We Trust. We've got this from Raid Wahid. I'm probably mispronouncing that, apologies, but the comment says, "This rocks. I will listen to this every time doing analysis now." Right on, brother. I'm definitely down with that. All right, we have from the notorious, the famous, the one, the only, Vanderhagen the Stampede. I hope you are doing well at the beginning of 2025. I spent the end of 2024 moving and reorganizing my new house, which was quite a big task, but also rewarding. Congratulations on your new house. It's a big deal. We're going to go to another Vanderhagen the Stampede comment. We have one here on... I have one. Okay, I like this one. We've got Vanderhagen the Stampede talking about Slavoj Žižek. We've got, you know, throwing in a little bit here of, how am I going to put this? We're tossing in a little bit of the late stage capitalism, critique of ideology. We're doing a little bit of an analysis here in this comment of Melania Trump. Very interesting. So this is like what I was saying in the video about how you could use psychoanalysis in application to political theory, or how, for example, even specifically Lacanian psychoanalysis, which is like a radicalized version of Freudian psychoanalysis, the key is to, at least to Slavoj Žižek, is to not ignore the libidinal repressed aspects of, you know, analyzing different political characters, let's say. So this is very interesting. Here we go. This is a real conversation starter, though. We have another Vanderhagen the Stampede comment here. I spent a whole month considering the nuanced terminology in differential geometry. For example, are the terms fundamental and form used appropriately? Fundamental clearly applies to the first fundamental form, which describes the intrinsic geometry of a surface, and the second fundamental form, which describes the extrinsic geometry, as these are truly foundational to the geometry of surfaces. However, it is less fitting for the third fundamental form, which serves more as a complement to the first two. The term form is consistently used throughout, reflecting their bilinear nature. I struggle to get consistency in differential geometry books in languages other than English. This is definitely a very good philosophical and linguistic issue that Vanderhagen the Stampede is bringing up here. In a previous video also, I said I was going to say, oh, I'm going to call him Vanderhagen instead, but then I never said that again. But then I'm not sure if the nickname that Vanderhagen the Stampede had is maybe the Stampede. So I just say the whole entire name. But the term form, of course, I'm thinking Plato first off, right? Because, you know, kind of kicking off the Western philosophical tradition, it wasn't directly written in any of Plato's dialogues, but it's kind of implied that he was working with a theory or a philosophy of forms. So you could say, if we have like a triangle, any triangle that I draw right now or that you think of in your mind right now, try to imagine that triangle without any subjective properties. And that's kind of hard, right? But we nonetheless feel like there is a concrete, maybe ideal triangle that we're constantly trying to get at when we say, oh, it's got three sides, the internal angles all add up to 180 if you're on a plane or whatever. And Plato, with this theory of forms, kind of kicks off what would later get refined in later with the German continental philosophy, so like Immanuel Kant and later Hegel, where you start to think of how do I put this? The idea sort of gets developed further, thinking about things like the difference between appearances and essences, because you could say any triangle that I draw or that you produce or whatever, that is in appearance, quote unquote, of a triangle, but we do not have access to the essence of a triangle. And that essence to someone like Immanuel Kant is transcendental. And Hegel then would go further and say that the gap between the subject and the other, the subject and the absolute, that gap is sort of like a window through which us kind of diving into that's a window for the transcendental to then come through, but we never get to access that because there's always a gap between the subject and the other, or the individual and the absolute, however you want to think of it. So this kind of thinking abstractly is rife throughout mathematics, and Carl Friedrich Gauss is no exception to this. And I think part of it is, okay, surely Gauss is a genius and one of the all-time biggest major contributors to all of math as we know it, but he existed within the culture that he lived in that time. And I think that it's just that it was like the vibe of math at the time to sort of develop in a track where you're kind of drawn towards thinking of your mathematical ideas as fundamental things, or there are these attributes to surfaces and manifolds or whatever that are these forms that we're dealing with these appearances of or particular instances of, but we can never get to this transcendental essence exactly. But that's what Gauss is maybe trying to go for, because ultimately we tack on the third fundamental form, right, in trying to neatly tie up the classical notions of curvature, right? Because the notions of curvature that Gauss was working with, where we have, I'll put, equations on the screen. I'm doing a horrible job just explaining this off the cuff, but modern differential geometry, and especially Gauss's student Riemann, sort of, kind of took things in a little bit of a different direction that we run with in modern times now, today. Anyways, another great comment from Vanderhagen the Stampede. Here was an interesting comment we have from Angierski Kali, probably butchered the name again, I apologize. But we have here, I'm not sure why you want to undertake this read out loud exercise. Perhaps this has been a successful teaching experiment for you. But I mainly wanted to say, as a physicist, which shout out, thank you to all of the physicists for watching. I did in fact use Kreisig as my first book on differential geometry, very interesting. I thought it very approachable and inspired me, along with the lovingly illustrated volume Gravitation by Misner, Thorne, and Wheeler, to select courses especially on general relativity while a physics undergrad. It was this funny coincidence that brought me here. Hope that was of some use. Yes, absolutely, because then we have another comment here, which is by William Branch, 4283, amazing, hats off. I have enjoyed Gravitation by Misner, Thorne, and Wheeler, MTW, since I was a high school student when it first came out in 1973. Covers the physics up to that point, not so good on the math in my humble opinion. Yeah, my laptop is now sitting on top of a copy of Gravitation, Misner, Thorne, and Wheeler that I got on Amazon, because I think the proper way to really use this book is as a stand to put my laptop on to then read the PDF in. And I'm already definitely starting to gather that the math is not like at the level of Wald's general relativity, but there's way more substance to like the theory of general relativity, like what it's all useful for in Misner, Thorne, and Wheeler. I haven't really gotten into it, but oh yeah, another thing I was gonna say is, so my last video, episode 30, I was asking the question, can you learn differential geometry for general relativity with this book? And my answer was sort of no in that video, but it's kind of like a Hegelian no, because in reading this, I read other materials that then made me realize the particular nuanced shortcomings of this specific book for learning the specific details of general relativity. But it's like, differential geometry can be applied to things like ray tracing and computer graphics, which was like another reason why I was kind of inspired to learn just differential geometry specifically in the first place. So, but then because I didn't learn specifically maybe things about like Riemannian geometry, manifolds, determinant line bundle right off the bat with differential geometry, but I was led to find those concepts. It sort of is like, well, this book kind of did lead me to end up learning what I needed to in order to start to appreciate general relativity. You know what I mean? So that's why I say it was a Hegelian no. So I do agree with Anne Gajerski-Colley's comment here of like, yeah, it is a very approachable book. And so it's like, yeah, physicists out there, you can perhaps use differential geometry to learn. Anyways, it's hard to form sentences when the title of this book is Differential Geometry and then I'm referring to differential geometry as a subject matter. Anyways, hopefully you guys get what I'm saying. All right, so continuing on with the reading, section 73, interchange of the order of absolute differentiation, the Ricci identity. The value of the second covariant derivative depends on the order of differentiation. Of course, the order becomes immaterial if the Christoffel symbols vanish identically, and covariant differentiation is then reduced to the usual partial differentiation, as is the case when the surface admits Cartesian coordinates. The order of covariant differentiation is also immaterial in the case of the second derivative of a scalar. We first prove the following. Theorem 73.1. The first covariant derivative of a covariant vector is a symmetric covariant tensor of second order, if and only if that vector is the gradient of a scalar of class r greater than or equal to 2. The proof is as follows. The covariant derivative a sub beta comma sigma of a covariant vector a sub beta is symmetric if and only if a sub beta comma sigma minus a sub sigma comma beta is equal to partial a sub beta partial u superscript sigma minus partial a sub sigma partial u superscript beta vanishes. Here, the form of the right-hand side of the relation I just read is a consequence of the symmetry of the Christoffel symbols, for which we can refer to, from section 47, the relation for symmetric Christoffel symbols, where we have Christoffel sub alpha beta gamma is equal to Christoffel sub beta alpha gamma, and Christoffel sub alpha beta superscript gamma is equal to Christoffel sub beta alpha superscript gamma. The quantity on the right-hand side is the rotation of the vector a sub beta. It vanishes if and only if a sub beta is the gradient of a scalar. Denoting this scalar by phi, we have a sub beta is equal to phi sub comma beta. And the above relation for the symmetric covariant vectors becomes equivalent to phi sub comma beta sigma minus phi sub comma sigma beta, which is equal to partial u superscript sigma of partial phi partial u superscript beta, then minus partial u superscript beta of partial phi partial u superscript sigma, and this is equal to 0. We will now study the general case of the second covariant derivative of a tensor of arbitrary order. In this investigation, the curvature tensor will figure. Differentiating covariantly with respect to u superscript mu, the covariant derivative, for which refer back to previous section 70, we have a sub beta comma sigma is equal to partial a sub beta partial u superscript sigma minus a sub nu, then times Christoffel sub beta sigma superscript nu. Of an arbitrary covariant vector a sub beta of class r greater than or equal to 2, we obtain a sub beta comma sigma mu equals partial u superscript mu of a subscript beta comma sigma minus a subscript nu comma sigma, then times Christoffel sub beta mu superscript nu minus a sub beta comma nu, then times Christoffel sub sigma mu superscript nu. That is, a sub beta comma sigma mu equals partial squared a sub beta partial u mu partial u sigma minus partial a sub nu partial u mu, then times Christoffel sub beta sigma superscript nu minus a sub nu, then times partial u superscript mu times Christoffel sub beta sigma superscript nu. Okay, this is suspicious because we have a minus, but then on the next line we have another minus, which kind of seems like a typo, but anyways, I haven't checked this math by hand, obviously, so don't yell at me in the comments. Quantity partial a sub nu partial u superscript sigma minus a sub nu, then times Christoffel sub nu sigma superscript capital nu, closed quantity, then times Christoffel sub beta mu superscript lowercase nu, minus quantity partial a sub beta partial u superscript lowercase nu minus a sub capital nu, then times Christoffel sub beta lowercase nu superscript capital nu, closed quantity, then times Christoffel sub sigma mu superscript lowercase nu. Alpha sub beta comma mu sigma can be determined analogously. When the expression a sub beta comma sigma mu minus a sub beta comma mu sigma is formed, a great number of terms cancel out in pairs. The result is a sub beta comma sigma mu minus a sub beta comma mu sigma is equal to a sub capital nu, then times the quantity partial u sigma of Christoffel sub beta mu superscript capital nu minus partial u mu of Christoffel sub beta sigma superscript capital nu plus Christoffel sub lowercase nu sigma superscript capital nu, then times Christoffel sub beta mu superscript lowercase nu minus Christoffel sub lowercase nu mu superscript capital mu times Christoffel sub beta sigma superscript lowercase nu, closed quantity. Or, in consequence of the mixed Riemann curvature tensor, we have a sub beta comma sigma mu minus a sub beta comma mu sigma is equal to a sub capital nu, then times capital R superscript capital nu sub beta sigma mu. In the case of a covariant tensor of second order, we obtain similarly a sub alpha beta comma sigma mu minus a sub alpha beta comma mu sigma is equal to a sub capital nu beta, then times R superscript capital nu sub alpha sigma mu plus a sub alpha capital nu, then times R superscript capital nu sub alpha rho sigma mu. From this result, we obtain the corresponding identities for contravariant tensors by taking suitable inner products. Since g superscript alpha beta and then a subscript of comma sigma is equal to 0, for which refer to Theorem 72.1, which I read earlier in this video, in the case of a contravariant vector a superscript alpha, we find the relation a superscript alpha and then a subscript of comma sigma mu is equal to the quantity g superscript alpha beta times a sub beta closed quantity, then with a subscript comma sigma mu is equal to quantity g superscript alpha beta, then times a subscript beta comma sigma closed quantity subscript comma mu is equal to g superscript alpha beta, then times a subscript beta comma sigma mu. Applying the above relation to this expression, we obtain a superscript alpha sub comma sigma mu minus a superscript alpha sub comma mu sigma is equal to g superscript alpha beta, then times the quantity a sub beta comma sigma mu minus a sub beta comma mu sigma closed quantity, which is equal to g superscript alpha beta, then times a sub capital nu times r superscript capital nu sub beta sigma mu. Since we have that r superscript capital nu sub beta sigma mu is equal to g superscript capital nu tau, then times r sub tau beta sigma mu, and r sub tau beta sigma mu is equal to negative r sub beta tau sigma mu, for which refer to identities that are in section 46, we finally have the identity a superscript alpha sub comma sigma mu minus a superscript alpha sub comma mu sigma is equal to g superscript alpha beta, then times a sub capital nu, then times g superscript capital nu tau times r sub tau beta sigma mu, which is equal to g superscript alpha beta, then times a superscript tau, then times r sub tau beta sigma mu, which is equal to negative g superscript alpha beta, then times a superscript tau, then times r sub beta tau sigma mu. Hence, a superscript alpha sub comma sigma mu minus a superscript alpha sub comma mu sigma is equal to negative a superscript tau then times r superscript alpha sub tau sigma mu. In the case of a contravariant tensor of second order, we obtain analogously a superscript alpha beta sub comma sigma mu minus a superscript alpha beta sub comma mu sigma is equal to negative a superscript tau beta then times r superscript alpha sub tau sigma mu minus a superscript alpha tau times r superscript beta sub tau sigma mu. And from the relations that we had just obtained, in the case of an arbitrary mixed tensor, a with subscripts alpha 1 through alpha r and then superscripts beta 1 through beta s, where this arbitrary mixed tensor is of class r greater than or equal to 2, we obtain a with subscripts alpha 1 through alpha r and then superscripts beta 1 through beta s, and then that arbitrary mixed tensor then has a subscript of comma sigma mu, then minus a similar arbitrary mixed tensor, but this time it has a subscript of comma mu sigma. This is equal to, again, where we have these equations running over multiple lines and we have a minus followed by, on the next line, another minus, which, if you know anything about math, negative times a negative equals a positive. Subtracting a negative is the same as adding the magnitude of that negative value. This is elementary school arithmetic here, but anyways, the sum on the index row from 1 to r of a with the subscripts alpha 1 through alpha rho minus 1, and then capital nu, and then alpha rho plus 1 through alpha r, and then we have superscripts of beta 1 through beta s, then times r superscript capital nu sub alpha rho sigma alpha, and that's the first sum. And then there's a minus sign, but then we go to the next line and there's another minus sign. So like I said, slap on my wrist for not diligently checking the math beforehand, but take this for what you will. Minus a sum on the index tau from 1 to s of the arbitrary mixed tensor A with the subscripts alpha 1 through alpha r and the superscripts beta 1 through beta tau minus 1 and then capital nu, and then beta tau plus 1 through beta s, and then this is times r superscript beta tau and subscripts capital nu sigma mu. And we know we're in Riemannian geometry because the relation that I just read is called the Ricci identity due to Gregorio Ricci Cubastro and Levicevita, Tullio Levicevita. So that's the end of section 73. Like I said, next video is going to be section 74, which is all about Bianchi identities. Got the fit. Going with cufflinks. We got the black leather, gold medal. I call this outfit John Foster Dulles, and I'll see you guys in the next video.